Hello, my name is Wayne Mattingly. I'm the proprietor owner of Whammer Labs, and this is about Wayne-O-Matic's Research Lab. That's what Whammer Lab stands for. I have a couple degrees, 30 years of semiconductor experience, and I've always wanted to know what the truth were surrounding C60 structure. C60 is the carbon allotrope formation with six-sided carbon. And what practical uses are there? I heard all this stuff about the different structures, but I never saw them put to use, so I wanted to go find out myself. Feasibility, practical cost, and uses. 10 years ago, a gram of this material was very, very expensive for me to experiment with. Now I play with a gram like it's nothing. They've gotten grams down to reasonable prices in comparison. I wanted to make a conductor that was electrically conductive, thermally conductive, all metal, 100% metal, all organic, all polymer, no metal, 100% organic, and non-toxic products and non-toxic process. I wanted a plastic that didn't shed when I put it in my hands, didn't leave marks, black marks in my hand, and I wanted a product that I could possibly make float. Here's additives, different additives that can be added to change the properties of the. Here's the standalone polymer, the Con 75 in this photo. Con 75 is the standalone. All of these are less than 1 ohm per centimeter cubed. Here's a copper bar. Here's silver, which is the most expensive. And now the least expensive would be the silicon additive one. It performs very well. It's right at an ohm per centimeter cube. The Teflon's just below it, and then the allotrope, the polymer, standalone with no metal, just the polymers and plastic, and its highest concentration form is right here, which is these four are less than 1 ohm, and everything that's tungsten. Here's the moly. Here's aluminum oxide. Here's a glass filler, silicon. Here's a nickel. Here's cerium oxide, so I wanted to make a polished medium type thing. Here's aluminum, and here's concrete. And the resistivities follow. These are around 5 ohms, the aluminum, cerium, and the nickel. The aluminum oxide is around 3 ohms. These are tungsten metal. These three are around 3 ohms. This is around 2 ohms. This is less than 1 ohm. This group here, the TFE stands by itself at 2 ohms. And then when you get 5 ohms and above, you use the cerium oxide, aluminum, and the concrete. Okay, now workability. I want something gluable, machinable, something that's electroplatable, and possibly wave solderable. I was able to accomplish wave solderability with this. If you put your soldering iron on the material, it'll wick out the solder, the copper particles. So what you want to do is you want to this is a very good weld, by the way, and very good solder, and it was a wave soldered. So then we have a low abrasion resistive plastics that are loaded with aluminum trioxide ceramic, and this one was charged. This one was charged with oil, 1 gram. It was charged with Prolong engine additive oil. This here is this is the material with no metal, and I achieved my goal of making it highly, highly conductive. I can run a blow dryer through these in series with these, and they won't burn up. 12 amps, by the way. And here are some foam conductors. I want to make a lightweight conductor that I could put around some 1-inch pipe. And I wanted to make it where I could heat it. So if I put power here, I start to heat this block. And to seal this block, it has to be painted to seal it. Otherwise, it floats and it's porous. Here's the heaters. Here's some organic heaters. This is an interesting heater here. Here's the aluminum square pad, and you can see the pad and the block here as it's completed. But this is a very simple construction. Here's a heater material that I can change its value by the process by which it's made. And then here's a copper screen, so that this side has, well, in electronics take the shortest distance, so it'll take the distance straight across to the plate, but that's grounded. And then we just make the plate, hook up some DC power, 12 volts to it, and it'll boil water. Okay, here's a organicrete. Now this stuff's magnetic, a magnet will think it, but it's paramagnetic. I put down as paramagnetic because it can't be made a magnet. It's thermally and electrically conductive, and it's heavy, and it can boil water. It's mostly iron, and it's a very strong adhesive as well. It wants to be a metal adhesive, metal to metal. With so this would be a metal to metal adhesive with conduction between, where you glue two pieces of metal together. And here's my high performers. Here's just some specs. Someone can bore themselves by reading through them. Here's the no metal products over on this side, and then the metal additives. Organostin's a tungsten additive. Organoaluminum is aluminum. Organic copper is obvious. Organonickel. Organilver is silver added. Organerium is cerium, and organomoly is molybdenum disulfide added as a dry lubricant. And then, so this is a lubricating plastic, and this is a tin, and this ceramic, and organobium is a niobium plasticide polymer, and all of them are I've been able to achieve as low as 0.014 per centimeter cube materials. And over here, would that include no metal at all, or the organic conductor, the organicon is what I call it. And organoflon is a Teflon loaded, silicon is a glass loaded. This glass is a pharmaceutical glass, the type that you can eat, that kind they put in ketchup to thicken it. And then organofoam, organoglue, and the heaters do contain actually metal, but the heater material does not contain metal. And for continued research, here's some pucks I made where I can inject. Here you see here and here. This is where a syringe is used to inject chemistries into. The baseline resistivity is noted on the outside. And here's what we do with them. We have some slides that we're also working